Alright, so this is Pencast5, I believe. Yeah, 5. Alright, and it's problem 2 from problem set 5. So for part A, we're given a cylinder where the current is running down. It's radius A, and the surface density, or the volume density, is proportional to r squared. We're going to call it equal to J not r squared. J is also equal to di over dA, perpendicular. And so J dA perpendicular equals di. I'm going to start writing dA perpendicular is just dA. So the integral of J dA equals the integral of di. So I equals the integral of J naught r squared. dA is the be dr times r d theta. So then I is equal to the integral from 0 to a, the integral from 0 to 2 pi j naught, I'm going to pull out front, r squared r cubed dr d theta, dr, my bad. So the d theta part's just going to pull 2 pi out, and then we get for r cubed dr 1/4 r to the 4th, 0 to a, 2 pi j naught times 1/4 a to the 4th. So I equals pi over 2 j naught a to the 4th. And I'm going to then go to j naught. Moving things over, we get 2I over pi a to the 4th. And then j just equals j naught r squared, so plugging that in, j gives us 2I r squared over pi a to the 4th, and in vector form, j equals 2I r squared over pi a to the 4th. Part B, we have a solid sphere, has a charge q, radius big R, it's spinning with angular velocity omega, and all it says it's rotating about the origin. It doesn't say, right, around the origin, or is it? Yeah, about its center, so about the origin. I'm just going to define that that's at theta equals 2 pi, or right on that central axis. So we're also given that Q is uniformly distributed. So now we got J equals rho V, V equals omega cross R, and also, since it's uniformly distributed, rho is just going to be Q over the volume, which equals Q over 4/3 pi big R cubed for the total enclosed charge. And so 3Q over 4 pi R squared cubed. All right, so plugging these in, J equals 3Q over 4 pi R cubed omega cross R. And then using law of sines, J equals 3Q omega R sine theta. Well, these are the magnitudes of omega and R now, over 4 pi R cubed. And since this was omega cross R, which was V, so J is in the direction of V, which is around the circle or in the phi hat direction. So then part C, we now have a disk still rotating. the way we defined it, we have omega coming out of the page, z direction, and we have a radius of r. So we have I equals lambda v, since this is I equals lambda v, and v equals lambda, okay, on the surface, okay. And v equals omega cross r. This time we have cross big R, because it's a line charge, so r is always going to be, little r is always going to equal big R. And then we have lambda, since it's uniformly charged, equals q over 2 pi big R. And then plugging in, I equals q over 2 pi big R omega cross R. And since it says to leave in terms of the parameters given, which was omega, big R, and q, this is where we stop. However, if we were to go any further with theta, we have q omega r sine theta over 2 pi r in the theta hat direction. R's would cancel, and I would be q omega sine theta over 2 pi in the theta hat direction. Lastly, part D, we have another sphere. It's rotating with angular velocity omega, and it has a sigma equals a cosine theta. K equals sigma v. Sigma equals a cosine theta. V equals omega cross r. So K equals a cosine theta omega cross r. Or if we go to magnitudes, a cosine theta omega r sine theta, and the phi hat direction, once again, it's in the direction of the velocity because k equals sigma v. And then rearranging everything just to make it look more pretty, we got a omega r sine theta cosine theta in the phi hat direction. And that is it. Done.